So now let's move to volatile memory in here, which is basically ROM. You can see in volatile memory in ROM, we're going to start by the historic construction of ROM, which is read-only memory. If you have a transistor, you do have a 0. If you don't have a transistor, the cell contains a 1. And the way you specify whether you have a transistor or not is by the manufacturer. So you write your code, you send it to the manufacturer would manufacture a chip that either has a transistor or it doesn't have a transistor. And once you have it, you can't actually do anything to it. You can only read it. You cannot change it. You can't add transistors to a chip. Of course, because this is a little bit of the problematic, maybe you're a designer, you just want to test a few programs before you actually send it to production, which actually is very, very costly. PROM was created, which is programmable read-only memory. What do I mean by programmable? Well, it turns out to be that the manufacturer shipped something we call a blank ROM. It actually will have a transistor in all the cells, but they added to the transistor what we call a fuse. Okay, and if you do not want a transistor because you want the cell to have a 1, you just basically break that fuse like here. So you blow that fuse up and now you have a 1. If you kept it intact, you have it a 0, and this way you programmed it, okay? So you have now read-only memory, but you can program it at least for the first time as a designer. This also evolved later that we have something we call an Eeprom, which is erasable programmable read-only memory. And the way it was erased, I'm simplifying it a lot in here. These fuse were then moved to something like a photoresistor or something like that. And you can basically, like if you blew a fuse, you can actually make it back intact. And the way you do it is by putting it under a UV light for half an hour or a certain period of time, which is actually very slow in today's standard. And then you do have another blank ROM again, and this is why it's called erasable, because you can erase it. You can actually rewrite over it by blowing other fuses if you choose to. Of course, this is very slow in terms of putting it in a UV light. The chip had like some sort of like, I think it's a chip, and it had a window in the middle. You actually remove it, you put it under UV light, and you just remove or you erase it. So then an electrically erasable programmable read-only memory was created, and it's electrical because you can blow the fuse or make it back intact just electronically, and that's pretty quick. And this is what we use nowadays. I think flash is a type of EEPROM, the one that you have on your USB. And if you think about it, like if you don't have power, that's it. The fuse is blown or the fuse is intact, you do have 1 or 0. All you have to do is just connect the power and you have your 1s and 0s back in, and that's how we have it in ROM. So sometimes instead of putting the transistors, whether you have a transistor or not, you can see that ROM sometimes is represented in this particular dot notation. In this particular dot notation, what we have is we have an address, and then whenever we want a 1, we put a dot. Whenever we want a 0, we keep it empty, basically no dot. So let's assume that I basically put the address 01 in here. You can see that I have 1 here, I have 1 here, and I have a 0. So effectively, I am reading 110. And that's how that representation is. This is very useful because if you think about it in here, and we, instead of putting these dots, we decided to put OR gates in here. Okay, look what happens. So we're going to put, again, I'm going to specify the exact one here. 0, 1 happened to give me 1 in here, 1 in here, and 0. Okay, I can do the same exact thing, and it will do it. I can basically put 0, 1 in here, and I will definitely get 1, 1, 0 in here. But what the OR gates give me is the following. I want now to focus on the following in here. So what you do is I will focus on data 2 in here. So 2 dots meaning this dot and this dot is connected to this, or this dot and this dot. It's basically the same exact thing. All right, so for data 2, let's assume that this address is actually A and B in here. And I decided basically to have 0, 0, 1, 0, and then 1, 0 in here and 1, 1. So if you have a 0, 0, what do you have? Well, this OR gate in here, this, like if you have a 0, 0 in here, you're going to see this here. This OR gate does not do anything because it doesn't get anything. So this OR gate will give me 0. So I'm not going to write that data 2 in here. I'm just going to write whatever it's asserted. Again, you're going to see that in here and in here, basically whenever it's 0, 1 or 1, 0, that OR gate will give me the following. It will give me a 1, okay, because it's asserted. This is asserted or this is asserted. That means that will be a 1. So if I'm rewriting this here, I have AB plus, or AB prime plus A prime B. That's what I actually have. And of course, the last case in here, which is 1, 1, you're going to see that it's actually not connected to the OR, so I'm going to get it as that. So if I write data 2 in here equals, you can see that that data, I was able to implement a combinational circuit in here. That's what I was after. So this particular decoder is actually generating the minterms, all the canonical minterms, all the minterms for the AB, all of them, A prime, B prime, A prime, B, A, B prime, A, and B. Okay, and what I'm doing is I'm taking some of the minterms, so I have some of products, and I actually will implement it in here. I'll have it. And if you probably know your digital logic, you would probably know that this particular data 2 is an XOR. It's only asserted when A and B are different in here, so it's only that way. So you might be wondering, why would I implement like a very simple gate using ROM? And the answer is the following. Here, what we have is we have only 2. You might have 1024 of these. This particular table becomes extremely large to actually track using gates. So what you have is you can actually just store it in ROM. And in ROM, basically, all you have to do is just, like you basically put your ones and zeros in the first column. So you're going to have 1024 rows, and the output you need, you put 1, 0, 0, 1, 1, 0, whatever you put pattern you want, and you have 1024 of them. And this is just one exact logic function. If you want more logic functions like we have in here, you're going to put 0, 1, 0, 1, and basically this particular row will give you another function like in here. So take a look at this one in here and figure out what is it, what type of gate it gives you. Maybe it gives you a gate, maybe not. This one here, for example, is very simple. We can see it, the data 0, and if you think about it, it's only asserted when it's 0, 0, and that's a NAND. So data 2 is an XOR, data 0 is a NAND, and of course you can actually store other gates in here. So take a look at that one here and fill it out, for example, at home, and you'll see what type of gate this actually will give you at Y. So you can think about the whole thing in here as a combinational circuit. You have an A, B as an input and Y as an output. Each column will give you an output. And A and B, because I have 2 of them here, so I have 4 rows. But if I have more inputs, I'll have 2 to the power number of the inputs, 2 to the power n, that is. Okay. So using logic arrays might save you some time in terms of like if you have very large arrays. And generally speaking, when you implement a combination logic using memory like this, what we call it, the table we get is what we call a lookup table, because you're actually looking in a table, the output Y in a table, as opposed to implementing it using logic gates.